All right, the number of participants is pretty stable. We have 2 minutes after 5. Welcome, everyone. It's great to welcome all of you to this webinar. I've been asked by Chipmetrics to give a seminar or a webinar on computational modeling of ALD. That is sort of one of the core research areas, and I see some familiar names in the list. It's really nice. Special welcome to Phil, former co-worker. Good to see you. So want to see what the group is doing after you left. Right, so my name is Ralf Tonner-Zech. I'm professor for theoretical chemistry of complex matter at the University of Leipzig in Germany. And I want to give you a very brief introduction into the group. So we're a group of computational chemists. Here you see us organizing the Area-Selective Deposition workshop in March this year in Leipzig. And we are situated in Leipzig. If you're not familiar with the German environment, it's around about 1.5 hours south of Berlin. And it's a very beautiful city if you ever want to visit it. Our group is working on different areas of computational chemistry, ranging from molecular structure to functionalization of surfaces up to solid state and material science. We're more of an application-oriented group. We're not so much developing math in some aspects, especially chemical bonding. We're also doing so. And you see here atomic layer deposition as one of the subtopics. And it's sort of getting more and more strong in the group since there's also a lot of interest from the community. Why are we doing this? Let me give a brief introduction. I assume that most of you are familiar with ALD. Nevertheless, I assume some of you also might not be and might want to know why should we take care about this. And I'd like to sort of really start with the big topics, with the grand challenges, more efficient solar cells, smaller transistors to get smaller devices, more efficient lasers, more efficient LEDs. That is something which is driving sort of the progress in human technological development. And one of the key factors which is behind this is moving towards more efficient microelectronics, and that usually means smaller microelectronics. So this is one of the many possibilities to visualize what I mean with that. This slide's been taken from Intel. You find this, of course, from many other companies. And this shows sort of the smallest size of the features on the current on the current chip. Of course, these numbers have to be taken with a grain of salt because they're also partly marketing. But what is really true is that the devices are getting smaller and smaller in their features, and we're approaching what many people call the angstrom era. That means that the features that we have in our microelectronic devices are so small that we can actually start counting atoms. And that's where it becomes interesting, because how do we actually create such devices? If you Google or if you do Wikipedia, that's how a transistor is pictured there. But of course, this is not the transistors that we are working with. So if you look into your smartphone or on the screen that you're currently using to look at this webinar, then the transistors in all these electronic devices are more looking like this. So they're really small, intricate, often 3D structures which have very small feature sizes. And this is a transition electron microscopy picture from a few years back, which shows already a 5 nanometer gate length. How do we produce this? The current major technology is lithography. With lithography, you have some sort of resist and the mask, and then you use light to sort of burn the features into your resist, and then you can sort of either do it in a positive or negative way. And in this approach, you can create the structures that you need for your microelectronics. To do this, if you want to approach the angstrom area, then you need these really expensive extreme UV devices that only one company in the world can produce, and that costs you hundreds of millions of euros. And even then, you are limited at some stage by the wavelength. So it's a very expensive way to produce it. It's still the major approach because it's a very established industry, but of course, this industry also always thinks ahead, maybe 10, 20 years in their roadmaps, and it's clear that this will not be able to be continued forever. So alternative approaches are sought for. And of course, if you do something top down, you can think about doing it bottom up. And bottom up in this case often means atomic layer deposition. We will talk about this on the next slide, what that means if you're not familiar with it. For the moment, it is a rather cheap way to produce or to create these structures from the bottom up in a chemical process, allowing you atomic control over the features in principle that you're creating. What is atomic layer deposition in a bit more detail? It is a surface chemistry-driven process where we have precursors which are selectively adsorbed on the surface. And the whole idea is that the precursor, which is shown here on the top left-hand side, is some sort of molecule carrying the atom that you want to deposit, for example, aluminium on silicon or on silica, and it only reacts with the surface and not with itself. So it's a self-limiting surface reaction, which then creates some reaction byproducts. And thus, with extended exposure, you reach saturation. And so you have a limit to what you grow, and this is how you control the thickness of the films which are created. And in a next step, after purge step, which purges away your reaction products, in a second half cycle, you have a second precursor, often called co-reactant. It's often water or oxygen or ozone. And this co-reactant, in an ideal way, only reacts with the first layer of molecules on the surface. And so if you follow this ideal reaction, then after 2 cycles or 2 half cycles, you created 1 layer of new material. The reactions are self-limiting, which is sort of the core feature of atomic layer deposition. Okay, what is it used for? Just one slide on the overview, because that's not the main topic of this talk. This is a very nice representation from a website. If you don't already know it, I would bookmark it, atomiclimits.com. It's a wonderful repository run by Evan Kessels in his group in Eindhoven, which summarizes and brings together the best works, literature, and also really, really interesting figures. And here they show where ALD is currently being applied. So it's all kind of technologies. Often it is some sort of coating, but sometimes it's also the technique which is used to create the structures which are actually the functional structures. Why do people use ALD and not other deposition techniques? Of course, other deposition techniques also have advantages, but ALD has some core advantages. And the 3 core advantages are summarized here. The first is the uniformity. You get films which have a very well-defined thickness over the whole range of deposition area. You can control it. You have growth control with the number of cycles that you use for deposition. And this is a major feature at the moment, you get conformality also in high aspect ratio structures. So if you have some sort of 3D structures, which is currently getting the norm, for example, in memory devices, then many of the faster deposition techniques reach their limits because they can't do it conformally, and ALD is pretty good at that. Okay, some of the sort of interesting things about ALD is that, of course, you have to optimize the parameters which are used in the experiment to do the deposition, and one of the key parameters is temperature. And this is sort of the slide which is slowly transitioning to the atomistic picture where we work with our methods, because what is happening with temperature in an ALD process? So what you want is the blue area. You want controlled ALD growth. And you need a certain temperature to do that. That temperature must be high enough that the reaction can actually take place so that the reaction barriers overcome, but not too high so that you don't have side reactions. So at too low temperatures, it might happen that your precursors don't react at all with the temperature because the reaction barrier cannot be overcome. Then you don't get any growth at all. Or it might be that it is too cool on the surface so that your adsorbats condensate and make some sort of undefined condensation product on the surface. If the temperature is too high, your adsorbats might also not adsorb because they desorb instantly before they can react with the surface. Or you can also have decomposition and uncontrolled growth of some sort of decomposition products on the surface. So that already gives you a first hint that you need some sort of atomistic idea of what is actually going on at the surface to really understand what's going on in ALD growth. One area which is currently under heavy investigations, especially in the microelectronics industry, and where we are also very active, is area-selective ALD. It's a one of the modern variants of ALD, and it's summarized here very simply. You have two surfaces or two substrates, which are just blue and green in this, and you want to do ALD on the blue area, but you do not want to have ALD growth on the green areas. That's the whole principle. And so you want to grow this red material only on blue, but not on green, and ideally you have a sharp edge here. So how can you do that? And I'll tell you in a moment why we want to do this for certain applications. There are several ways to do that. The first is sort of intrinsic reactivity, selectivity. So we have the normal ALD process, but now our precursor has a chemoselective reaction to the surface. So it only reacts with the growth surface and not with a non-growth surface, so you have an intrinsic selectivity of your precursor. This is something that many people wish for, also in the application, because you don't need an additional chemical species. Unfortunately, it very rarely works, because usually the chemoselectivity, you need certain combinations of substrates to be able to do that. And also the chemoselectivity is always limited. So usually these approaches only work for a certain amount of ALD cycles. So what is more commonly done is activation of the growth surface. So this is a second possibility. So with some sort of electrons or plasma or other electric fields, you try to activate one surface so that it becomes more reactive. But the by far most important approach at the moment is deactivating the non-growth surface. So you block the non-growth surface so that you can do selective ALD on the growth surface. And this deactivation is done chemically. And it is done by using an inhibitor molecule, which is shown here, which is sort of deposited on the non-growth surface before the ALD growth takes place. This can either be done once here in the middle, or it can be done in every cycle, and this has been termed ABC type ALD by the microscope. And so now you have a blocked surface, and then you can selectively deposit on the second surface. Why do people want to do this effort? The so-called killer application for area-selective ALD is the so-called ideal via. So what you have, if you have some sort of transistors, you have to somehow connect them in a certain dimension to be able to sort of give current to a certain type of your transistors. So you have bottom metal lines that you somehow have to connect to the top metal lines. And to do this, you use a connection which is called a via. And what you want to have, if you sort of turn this around, is you have your bottom metal lines, the top metal lines, and you want to have this connection being straight and ideal between the two metal lines. And this is usually embedded in some sort of dielectric material. And what happens while you're etching very often is that you get the so-called edge placement error. So if you try to etch very, very small structures, you might make very small mistakes in the etching. And this small mistakes leads to this non-ideal via, where the via is somehow a bit misplaced. And the main problem here is that you get that side effects. For example, you get electron tunneling because suddenly the via is too close to the next metal line. This gives sort of problems in your device performance in the end. So how does area-selective ALD help here? Now what we can do is, if we have a selective ALD process which blocks the dielectric, then you can do deposit ALD on your metal surface, and you get the self-aligned via. So by this area-selective ALD, you only get growth where you want it, and then you can prevent this electron tunneling from happening. And actually, there are first publications, for example, TSMC published in 2021, the first real sort of manifestation of this fully self-aligned via. Okay, this is just the application side, but we're theoreticians, so we don't build devices, but we help understand things. And one of the things is what are the inhibitors that we ideally use? And here you see two typical inhibitors being used: small molecules and self-assembled monolayers. And so self-assembled monolayers were the first generation where people actually used these long chain alkanes with some head groups to attach them to the surface, mainly been done by Stacy Band and Boram Lee. And it turned out they are very good blocking layers, but they have disadvantages because you need solution chemistry to apply them, and they're often impossible to get rid again. And you want to get rid of your inhibitor layer again. And so the next generation is the so-called small molecule inhibitors, where this tail group, the blocking group, is just much smaller. And sort of one way to emphasize this is a wonderful graphic by my coworker, Dr. Fabian Peek, who showed that it's essentially the same chemistry. So you have head groups, then you have some sort of chain which is blocking, and then you have a tail group. And the only big difference is that SAMs have these long linkers, and small molecule inhibitors have short linkers. All right, so that's how we do this. And that's the possibility for doing area-selective ALD with these small molecule inhibitors. You put them on your non-cross surface, then you do ALD, and then you try to get them off again. Okay, these are some of the molecules that we investigated in the last years, mainly together with Boram Lee and Stacy Band, and I will show you two examples of our work on how theory can support experiment there. Okay, what are the atomistic details which are important in this process? And so one of the major questions is, how does this SMI actually block the incoming precursor? So there are different possibilities. So for example, what happens is that we have only growth from the precursor at this reactive surface sites, and we can sort of deactivate this by the inhibitor, and then we call it chemical passivation. So the OH groups are very often the reactive groups on many surfaces, and we just block them with the inhibitor so that the precursor cannot react with them anymore. So this is really the atomistic detail of what's happening at the surface. A second possibility is that this inhibitor has sort of these blocking tail groups which prevent the adsorption of the precursor to happen. So the precursor cannot reach the surface anymore. And it either cannot reach the surface anymore, this is what we termed adsorption prevention, or if it reaches the surface, it cannot react anymore because there's just not enough space, and we call this reactivity reduction. Of course, one question is also, in every experimental area-selective ALD, people see that the selectivity is lifted after a certain number of ALD cycles, and it's experimentally impossible to find out what is the degradation mechanism, what is actually going on. So this is also something where computations can make a difference, because we can investigate the selectivity lifting reactions on an atomistic level. So for example, with intrinsic selectivity, we can have imperfect chemoselectivity, so we can compute competitive reactions of the inhibitors on two different surfaces. And with inhibitor-based area-selective ALD, we have three major sort of selectivity lifting reactions. The first is that the precursor chemically attacks the inhibitor layer and destroys it. And this is often the most important one. But also, it can be that the inhibitor layer is not perfect. So the density of the inhibitor layer is a key feature of every area-selective ALD process. And then the precursor can penetrate this layer and reach the reactive surface sites to start the nucleation. But it can also grow on top of this inhibitor layer. And all these mechanisms are in principle possible. Now you could ask yourself, okay, that's nice, but why should we use computational approaches to understand this? I gave you already one example. There are some things that we cannot access experimentally. That's where theory can make a difference. But if ALD would look like this is taken from the iconic review by Steve George from 2010, then we wouldn't need computation. So if ALD would look like that, would be as perfect as that, we don't need it. But that's more how ALD looks like in practice. There are a lot of side reactions. There is sort of reactions maybe between the precursors, between precursor inhibitor. There is surface defects. There's incomplete growth at the surface. there's diffusion, there's all sides of side reactions going on. And this is actually determining the quality of the ultimate film in the end. And to really understand this, or to really improve the processes, we need to understand what are the detrimental processes at an atomic level. And that's where theory can make a difference. So one approach that we developed to this SMI-based area-selective deposition is schematically shown here. So in the first step, we can investigate the chemoselective absorption of these inhibitors on the non-cross surface versus the cross surface. We can understand for several inhibitors which one absorbs best to the surface and why. We can understand the bonding to the surface. And then the next step is often very important. What is the best, or what is the maximum density that an inhibitor can have on the surface? Because that determines if a precursor can penetrate the surface or not. And this maximum coverage is also very hard to determine experimentally. And then in the last step, we can have a look at the decomposition reactions. So what is really sort of making this inhibitor layer stable, or how can we maybe chemically modify it to make it more stable? And we studied several of these systems in the past, so on metal surfaces, dielectric and oxide surface, and recently reviewed all these efforts and all the efforts from the community in this chemistry of materials review. So also, if you have want to know a bit more about some of the theoretical methods, I can briefly touch them today, but in this review, we sort of try to explain to non-theoreticians what these theoretical methods can be used for in ALD modeling. Okay, this leads me to the computation methods, because of course, I assume that most of you have an experimental background in ALD. You might want to know, okay, what can computations actually give me? And that's what I want to show you in the next minutes. So what is the methods that we have in ALD modeling? First, what is this field about that we are talking about here? We usually talk about theoretical chemistry for the whole field of using computers to investigate chemistry, and mainly for method development. This is not so much relevant for ALD. What's mostly relevant is computation chemistry. That's application of these theoretical methods to really understand chemical questions. And quantum chemistry, we call it when we use quantum mechanical methods in chemistry. What does that mean? Quantum mechanical methods, we have essentially three paradigms for theoretically describing chemistry. And the first one is sort of the oldest one. This is classical mechanics. Here in the middle, we use Newton's equations, force on the nuclei, and we essentially neglect the electrons, or we treat the electrons as some sort of parameters in our classical mechanical investigation. This is often done for very large scale calculations. For example, for peptide modeling, people use force fields. What we are mainly dealing with is quantum mechanics, and there we usually treat the nuclei still classical, but we treat the electrons as sort of quantum particles. One could also say a wave-particle dualism, which is sort of a description of what's going on, because electrons behave quite weird, and the most weird part is that we have to describe them with this sort of wave-like equation, the so-called Schrödinger equation. So this are the two sort of historically grown processes, but then we have a pretty new third paradigm, and this is data-driven approaches, so everything connected to machine learning. I will not talk about this today. This is still in progress, but you can ask me in the Q&A if you're interested in. And here we try to get some information from the data and via correlation statistical approaches. What we most often do is that we don't care about the quantum nature of nuclei. This is mostly neglected with some exceptions, and we use the so-called Born-Oppenheimer approximation. And then we can end up with really drawing these reaction coordinates and potential energy surfaces for getting thermochemistry and reaction barriers, which tell us something about, is it feasible that reaction takes place at certain temperatures? Okay. This is a very typical theoretician slide, because it shows you these are the types of methods that we have available. So on the x-axis is the size of the system that we can treat. On the y-axis is the dynamical range that we can treat. So from femtoseconds to milliseconds. We are down here, in the quantum chemistry part, that is where most of the work of our group is going on. So we can treat hundreds, or maybe if we push it, thousands of atoms for a rather short period of time. And this is where we can actually look at electrons. And this is usually crucial for ALD modeling because we have bond making and bond breaking, and we have to have a detailed understanding of the surface chemistry to really know what's going on. If the electrons are not so important, we can use force fields, and there we can sort of neglect the electrons and only look at the interaction between atoms. And this, up to recently, was only possible without investigating bond making and bond breaking. And currently, machine learning is interrupting this field, or it will change the field forever, because machine learning based force fields are currently entering the scientific field, and they will enable in the future to have DFT quality large scale simulations on a dynamical range. Okay, but this is still a work in progress. And if we want to go even larger, we can do mesoscopic models. There we even lose the atomistic structure, and continue models. That's something if you want to model a reactor and read the flow of your precursor in the reactor. Fortunately, it turned out in the last 20, 25 years of ALD research that we do not need to care about the reactor. So the flow of precursors doesn't really matter. So we can really just focus on the local reactions of the precursors, which makes life a lot simpler compared to, for example, heterogeneous catalysis, where we would actually have to do this. Okay, this is another type of this method slide, but now geared towards atomic layer deposition, because what we have here are the methods which are typically used in atomic layer deposition modeling. So if we really want to know the chemical reactivity, we are here in this on the left-hand side. I will talk a bit about the functional theory in a moment, but of course there are other methods that we can use, Hartree-Fock or post-Hartree-Fock methods, which are virtually not used at all in ALD modeling because they're just too expensive in terms of the computational time that you need. We have the force fields, and here we already included machine learning as a new paradigm for revolutionizing this part very shortly. And one thing which is very important in this field, we'll briefly talk about it, is RSA or KMC-like approaches. So we will really model the adsorption of molecules on a surface grid. And as I said, this post-molecular resolution is luckily not so important for ALD modeling. What is important often for us is the dynamical behavior of the system. So we call ab initio molecular dynamics when we look at the development of the system in time by using a method which is accurate enough to capture electrons. So for example, DFT. We can only do picoseconds, which is of course tricky because it's a very short period of time and not all the crucial reactions are happening in this time. Some words about density functional theory, because I would say it accounts for 98% of the computational studies in areas in atomic layer deposition research. So I told you before that we need the wave function to describe these electrons in a quantum system, a molecule, for example. But we can also use the electron density instead of the wave function. This has certain advantages because the wave function is a sort of physically not touchable object. It's something that we don't really can say what the meaning of the wave function is, and we need sort of interpretation to understand what the wave function is. It's also a very complex property. The electron density is something you can measure. You can get this in some sort of diffraction, a high resolution diffraction experiment. You can actually measure the electron density. And so it's a much nicer variable. And it turns out that we can use the electron density to build a theory upon where we can get the energy in all the properties of a system. And this is called density functional theory. It was developed in the 70s by Hohenberg and Kohn. And we have some so the energy is a function of the electron density. That is the core new idea. So we can get all the properties just by knowing the density. And then we have three terms which we can get exactly. I only briefly mentioned it: kinetic energy of the electron, Coulomb repulsion, and attraction to the nuclei. And then is the interesting term because it's all the rest. So these three terms are exact, and this term is not exact because it captures all the complicated interactions between the electrons. And this is the infamous exchange correlation function, which is the core ingredient in every DFT calculation. So if you read the ALD literature, you will see that there's actually not much variety in the density functions that people use, but I want to at least show you that there are different density functions. They are historically arranged on this sort of kind of biblically inspired Jacob's ladder. So we have different classes of density functions, LDA, GGA, and so on. And they're sort of ordered here, but one important thing is that it doesn't mean if you go up one rung on this ladder that it really gets more accurate. In the ALD literature, people nearly exclusively use the so-called PBE functional. It's a GGA type function. It's a rather old functional, but it turns out that for surface chemistry, it's actually quite good. Very important is that you include dispersion correction because these density functions do not capture dispersion interaction. That is the attraction between two rare gas atoms, for example, so fluctuating dipole interaction. So the de facto standard in chemistry is the DFTD method. It's a very simple but very, very accurate or quite accurate semi-empirical methods, which can just be added as a correction term to your DFT energy. And as I said, there is hardly any sort of other approaches around in the ALD literature. Okay, sometimes you want to know how does your system develop in time. For example, you want to know, okay, if my precursor arrives on the surface, how long does it take until it actually reacts with some sort of surface groups? If you want to know this, then you have to use some sort of molecular dynamics approaches. So you get the time-dependent behavior of your system, and you use the Newton's equation of motion for your nuclei. You might remember we treat the nuclei as classical particles, so we can use classical mechanics to sort of treat their movement in time. You might wonder, okay, where are the electrons? And essentially, there are two ways to treat the electrons in this respect. So we only use this Newton's equation of motion for the nuclei. And the electrons in the force fields are completely neglected. They're only parameterized into the interaction between the nuclei. So we have components here in a typical force field. We have parameters, lots and lots of parameters according to the bond stretching, potential bending, rotation, and non-bonded interaction. So you need a huge parameter space to set up a force field. If we do so-called ab initio molecular dynamics, and this is the standard in ALD modeling, as I said before, with classical MD, we cannot model the breaking of chemical bonds, which is crucial in ALD. Then we use density function theory, for example, to describe the electrons instantaneously adjusting to the nuclear movement. As I also said before, a recent paradigm change is happening because currently people are using machine learning to sort of learn the DFT data and then sort of provide molecular dynamics, which is as fast as classical dynamics, but as accurate as DFT dynamics. And we hope that we can submit the revision of our current paper on this tomorrow. Okay, another class of compound or a class of methods which is important for ALD modeling is so-called Monte Carlo methods. Monte Carlo is a method, so it's a family of methods which relies on some sort of randomness, some sort of random numbers. And you see here an example from Wikipedia where you can use, which tries to visualize that you can use random sampling to essentially approximate an analytical function. So this is well known that we can use random sampling to approach an analytical problem. And we can use this, for example, in ALD modeling by using so-called kinetic Monte Carlo approaches. And so the goal here is that we want to model the system's development over time. For example, you want to know, okay, in a few milliseconds, how many precursors adsorb to the surface and how do they react with each other. And you need some sort of input. So you essentially need all the reactions which are possible, the reaction the reaction thermodynamics and the reaction barriers. So this is the tedious part. You first have to have a large scale DFT study to start with. And then you use essentially transition state theory and some sort of time evolution algorithm to get the temporal development of your problem. So the advantage over molecular dynamics is it's much faster. The disadvantage is you have to have this work at the beginning to get all the possible reactions. Because if you miss one crucial reaction in your set, then your kinetic Monte Carlo might give meaningless results. A simplified version of this kinetic Monte Carlo idea is a very popular method at the moment in ALD modeling. It's called random sequential adsorption. It's been put forward by Boam Lee as the first one, and then Atri Marcos also has their own implementation. And the idea is that you get rid of these transition states. So now you don't care about the reaction barriers anymore, but essentially what you do is you have some sort of random driven algorithm which has some pretty harsh assumptions about which possible molecular interactions you capture. So it's very simplified, but what it in the simplified manner models is that the molecules randomly adsorb at the surface and you get coverages. And one last thing which is important here is how do I set up a chemical model? And I just want to have one slide on this, but this is actually one of the major things where experience comes into play. How do I actually model the experimental system? Because very often ALD substrates are pretty complex and they often badly characterized. So people don't really know how their substrate looks like under ALD conditions. So in the computational modeling, we have to set up some sort of atomistic structure for the substrate. And so we have to make assumptions about, okay, what's the hydroxylation rate, grade of the silicon oxide surface? Or what is the facet of the copper? Maybe it is an amorphous copper surface in the experiment, or it's nanocrystalline. And so this is something which is really crucial, and I would also say a bit overlooked in the computational ALD literature at the moment, that we need sort of a good chemical model to represent the actual substrate. And in the last part of this presentation, I want to show you two examples of how we worked in the modeling of area-selective ALD. And the first one is these three compounds, nitrogenous aromatics. So the question was, if we put the nitrogen at different places in this aromatic ring, or even outside the aromatic ring, does this change the interaction with copper or copper oxide? It's the work together with Stacy Bent. They put this forward and did the experiment. Alex Shearer did the experiment, and they collaborated with us to try to understand what their results actually mean. So it is alumina ALD process with DMAI as a very typical precursor for area-selective studies. And they wanted to have the blocking of copper while silicon oxide should not be blocked. And so what we did is we investigated the SMI adsorption on this non-gross surface of copper. And here, as I said, setting up the chemical model, we choose the ideal copper 111 surface. So it is something which is very typical in ultra-high vacuum studies. And we just assumed, okay, this is the most stable facet of copper under this reaction condition. So we use this as a model. And you see that the three molecules adsorb in a slightly different way. So pyridine is lying down on the surface, quite strongly bonded, aniline. And pyridine has these two adsorption modes, upright and slightly tilted, which are very similar in energy. And pyrrole essentially wants to lie down because the upstanding is much less stable. And then after we did this, we asked ourselves, okay, well, it is ALD, so it will certainly be some sort of atmosphere around, or at least it's not perfect. So we will have copper oxide as well. So again, asking the question, what's a good chemical model? So we searched for reasonably accurate, but also not too complicated copper oxide models, and we ended up with this copper oxide 111 surface. And to summarize this, the energies are a bit larger, but they are actually, the trend is very similar to copper. Next step is, how can these SMIs pack on the surface? And this is now done sort of really using density function theory, sort of trying to get the optimal distances between the different SMIs on the surface. And that these numbers are very similar means that there's not much repulsion between the molecules at the surface. So we did this more systematically for the three adsorbents, and you see if they are far away from each other, they don't repel each other at all. But if they come very close at some stage, you have repulsion between the adsorbents at the surface. And this is sort of limiting the maximum packing at the surface. Of course, we need to check with the experiment, okay, does this help to understand the experimental data? And here you see the experimental data from Alex Shearer. And to summarize these ALD curves, pyridine shows no blocking, pyrrole and aniline have blocking on the copper. And so we went back into our theoretical data and tried to find, okay, what is the difference between pyrrole and aniline on the one side and pyridine on the other side? And the only difference is that we have upright standing pyridine, but we have lying down pyrrole and aniline. So the lying down seems to be crucial for the blocking of these SMIs. And in a subsequent study, Fabian investigated this mechanism with random sequential absorption. It's a new algorithm that he's currently developing. And so you have to simplify the molecules, and then you can sort of visualize the results of these molecules on the surface. So you see you have quite large cells that can be covered with rather reasonable accuracy. And you can also sort of count all the runs of your adsorbate adsorption on the surface. So you can do thousands or even 10,000s of different runs to get a good statistical distribution. We can also get the covered area. This is the x-axis here. And this is the crucial information that we can compare to experiment, because the more areas covered, the better the SMI is blocking the surface. If we do this with the RSA, we actually get the highest value of coverage for the upright standing. So this was puzzling at first, but then we realized, okay, you have to include the tilting. So this flexibility of the pyridine to have different adsorption tilting modes on the surface, this really reduces the possibility for the next precursor to come in, and the maximum coverage of this SMI gets much smaller. Okay, so with this, we can sort of use the theory to explain why one precursor is not working very well and the other two are working well. Next, just two more slides, just to show you another type of investigations that we can also do, because on a very broad scale, the last study was interpretation of an experimental finding. And the next step is usually what we try to do is we try to give something back to experiment. We try to predict something new. And here we looked at dimerization of precursors, and this rather busy slide just summarizes that we used a different combination of theoretical approaches to get as accurate numbers as possible for the dimerization rate of precursors. And so why is it important to have very accurate numbers? This is shown here in the lower right-hand side, because the dissociation equilibrium constant depends exponentially on the energy of the dimerization or the dissociation of the dimer. So if you make a small error in this dissociation energy, then you will make a big error in the equilibrium constant. And so we try to reduce all the known errors in these DFT calculations, and even added a layer of very accurate wave function based methods, which we can do because it was molecular calculations. And what we can end up with, and this is something that we can give back to the community, is a dissociated dimer fraction. This is a typical term that people are using to investigate, okay, is the precursor monomeric or dimeric? And we can compute this as a function of temperature using statistical thermodynamics. And thus we can see for different substitution patterns of this aluminum precursors, we get very different dimerization rates depending on the temperature. For DMAI, for example, is dimeric all the time up to very high temperatures, and the alkyl precursors very quickly dissociate at very low temperatures, and the chlorinated precursors are somewhere in between. So the gray is the ALD window. So it means depending on where you are on the ALD window, your chlorinated precursor might be monomeric or it might be dimeric. It's very important to incorporate temperature in the study of ALD processes, because if you look into the literature, that's one of the questions we got when we submitted this paper by a reviewer. I said, well, but it's known in the literature that trimethyl aluminium is a dimer. Yes, it is. At very low temperatures in the solid state, it is a dimer. But if you look at ALD conditions, it is not a dimer at all. It very quickly dissociates because of the temperature effects. And so it is important for all the modeling to incorporate ALD conditions. All right, with this, I'm at the end of my talk. Thank you for listening. And now it's the time for you to ask questions if you want to. Thank you for listening.